I'm the Philosophical Bachelor, and today I'm going to talk about Peirce's Metaphysics. From 1891 to 1893, Charles Sanders Peirce published 5 articles on his metaphysical ideas in the philosophical journal, The Monist. Peirce is a polymath genius born in 1839. He is best known for his work in logic, language, mathematics, and analytic philosophy, and is the founder of American pragmatism. His work on metaphysics was, however, considered by some of his commentators as a puzzling embarrassment. Nonetheless, it is what I want to consider in this series of videos. The plan is to make one video for each of the 5 articles, but we will have to see how things proceed as I write the synopsis of them over the next few weeks or perhaps months. While his writing is clear and the articles are not difficult to read, it still remains no small project, since the papers are philosophically rich, requiring me to often have to pause to try to understand and then connect his ideas. In these papers, he brings to the fore the role of chance and continuity, not just in our understanding of the world, but in the very becoming of things as they are today and will become in the future. Peirce is also a scientist. He graduated summa cum laude, which is the highest class of Latin honors, from Harvard University with a Bachelor of Science in Chemistry. Science is how he made his living, since his philosophical efforts did not really pay. He worked for 32 years with the US Coast and Geodetic Survey and briefly taught logic at Johns Hopkins University. Despite all that, he died in poverty at the age of 74. He did not write books, though he did write prodigiously, with his writings scattered across journals, some 12,000 pages. His unpublished writings are even more, some 80,000 handwritten pages. The journey of these pages is a tale unto itself, with many lost or misplaced, but happily, it seems some at least have been recovered. The Peirce edition project began in 1976, over 50 years after his death in 1914, to compile and present his extant writings chronologically with the ambition of releasing a total of 30 volumes. They have made 7 so far. It amazes me that we are sitting on a treasure trove of ideas from a mind of the first class, and yet as far as I understand, the Peirce edition project has been in limbo for almost a decade now, releasing its last volume in 2014 and nothing since due to funding issues. A century after his death, who knows what breakthroughs await humankind, or if the project has to be sadly abandoned. Since this is the first video of the series, here are the titles and dates of Peirce's 5 papers in the Monist, which covers his metaphysical ideas. January 1891, The Architecture of Theories. April 1892, The Doctrine of Necessity Examined. July 1892, The Law of Mind. October 1892, Man's Glassy Essence. And January 1893, Evolutionary Love. Today I will talk about the first of these papers, The Architecture of Theories. It introduces his metaphysical ideas, focusing on one of the 2 main elements in his process metaphysics, his idea of chance in the evolution of the cosmos. Peirce begins by making a brief survey of the grand systematic theories of the past. Some of these theories were incidental. Not a result of historical development, they were merely happy thoughts which have accidentally occurred to their authors, after which these theories were stretched beyond their rightful limits in an attempt to explain everything with them. Peirce compares this to building a house out of paper. It may be complete and its construction may be interesting and instructive to home builders, but is unserviceable as a place to stay. Other systems then try to reform these incidental theories because of the difficulties besetting them. Some of this second type may lead to revolutions, though the reform path is for Peirce like a partial house rebuilding. The tearing down of the bad parts may not be sufficient to rescue it, while not enough effort has been made to bring the new parts into harmony with the good parts of the old structure. Hence, according to Peirce, theories should neither be happy incidents then expanded into systems, nor reformists. They instead need to consider the historical development of thought and be deliberate in construction. Systems ought to be constructed architectonically, he writes. Like building a house, Peirce believes that preparatory effort is needed before one can even break ground. Thinking and planning is required before any actual theory construction should begin. The studies preliminary to the construction of a great theory should be at least as deliberate and thorough as those that are preliminary to the building of a dwelling house, he emphasizes. Those with the ambition to work on fundamental problems need first to make a complete survey of human knowledge, to note down the valuable ideas and understand what works and what does not. The aim of this preparatory work is to make a systematic study of the conceptions out of which a philosophical theory may be built, in order to ascertain what place each conception may fitly occupy in such a theory and to what uses it is adapted, he adds. To illustrate his point, Peirce looks at a mechanical philosophy which has been dominant since the time of Galileo Galilei, the 17th century thinker. Even today, a mechanical understanding of physics remains in place, except perhaps for specialists working in fields such as relativity or quantum mechanics. According to Peirce, Galileo's approach to theory development was mostly not experimental, contrary to how science is often conducted and perceived to be conducted today. Galileo began with a belief that common sense and il lumina naturale, the light of nature, is sufficient for scientific work because he always assumes that the true theory will be found to be a simple and natural one. Such an attitude remains with us today. A likely theory is one considered to be simple, symmetrical, mathematically elegant, harmonious, and economical. This attitude traces back to 14th century philosopher William of Ockham, whose injunction is not to multiply entities unnecessarily in order to explain a phenomena. Occam's razor has become de rigueur in theory construction, where between a more complicated theory and a simpler one, both capable of explaining what requires explanation, the simpler one should be preferred. However, Peirce is going to problematize this guideline, where theories and their features rightly or wrongly shape how we think about reality. Is the dog wagging its tail, or is its tail wagging the dog? For instance, in mechanics, the straight line is taken to be a basic feature of reality. A body left to its own inertia moves in a straight line, and a straight line appears to us the simplest of curves, he observes. In geometry, which is foundational to mechanics, the Euclidean axioms talk about straight lines as basic geometrical objects and use them to build the rest of its theorems. Yet in itself, no curve is simpler than another. Simplicity is something we attribute to objects based not upon how the objects are in themselves, but merely on what we believe to be simple or otherwise. Theories in Peirce's time posit that light travels in straight lines. As an aside, keep in mind that while we know this to be incorrect today, they did not. But why was light posited to travel in straight lines in the first place? Peirce suggests that it is because of the importance which the straight line has in the theories of geometry and hence of mechanics. Such conceptions then become implanted in our minds, which then guides how we formulate theories. Nonetheless, one good thing about such preconceptions is that they help us guess what may be the right scientific laws. If we did not have any preconceptions, we would have to search completely in the dark, giving us only a slim chance of chancing upon the correct law. For instance, if we had to guess how light travels but without suspecting it could be a straight line, there will be an infinity of possible curves to choose from. As the mechanical sciences become more and more entrenched in the 17th century onwards, thanks to the work of Galileo, Isaac Newton and their contemporaries, whose theories continue along the lines of mechanics, soon all physical phenomena became explained in terms of mechanical principles. However, as deeper investigations proceeded into more complex phenomena, additional hypotheses became required, and the possibility that these additional hypotheses were not simple cannot be ruled out. If we mark Max Planck's postulation of quanta in 1900 as the start of the field of quantum mechanics, Peirce has already suggested in this paper about a decade before that there is no reason to believe that behavior at the atomic level will obey the laws that work well at a macro level, that is, the laws of mechanics. The point that Peirce is making, contra Galileo and William of Ockham, is that there is no reason to expect the laws of nature to be simple. Moreover, even if light does travel in straight lines, our next question should be why? Karl Hamper, a thinker nearer our time than Peirce, proposed that the way we understand explanations in science is from a covering law, where a phenomenon is considered explained when its behavior can be traced back to a general law. However, this leaves the covering law themselves unexplained. Peirce considers this unacceptable, writing, "To suppose universal laws of nature capable of being apprehended by the mind and yet having no reason for their special forms, but standing inexplicable and irrational, is hardly a justifiable position. Uniformities are precisely the sort of fact that need to be accounted for." Peirce resorts to another metaphor to make his point. If a coin is flipped and gives a random result, this behavior does not call for an explanation, or the explanation will merely be that that is what randomness looks like. But if the coin kept coming up heads only, we will want to know why. Likewise, we need to explain the regularities of the laws of nature, the laws of science. Before going further, let us consider how law is commonly understood. Laws in a legal system are not immutable or cannot be broken, such as a law against robbery. Just because there exists a law prohibiting robbery does not mean that robbery cannot take place, contrary to the laws in science and of nature, which are precisely what we expect cannot be changed or broken. 10 out of 10 times, dropping a glass from a height onto a hard floor is going to result in it falling and shattering, a result of the law of gravity in action. Any student will have encountered many scientific laws in his studies, even if he only studied science briefly. Lentz's law on the refraction of light, Boyle's law on pressure in gases, Ohm's law on electrical resistance, Hooke's law on springs, Newton's 3 laws of mechanics are just a few taught to us by the age of perhaps 13. We are so used today to the idea that science gives us an accurate depiction of our world that we may think of such laws of nature as truth, correct, immutable, precise, and eternal. Back to Peirce, he asks, how can we account for the so-called laws of nature? His answer is evolution. Now, we are used to the term evolution being associated with biological reproduction. Other thinkers have also used the term to describe what happens within society, a survival of the fittest in accordance to Darwinian principles. But Peirce is doing something new here. He is thinking about evolution, not just restricted to mutations within the genes of living things, which is what Darwin is using the term to describe, but an evolution of everything, from the cosmos to the smallest of things. But before he explains that, he appeals to a phenomenon that any experimenter will have experienced. In a laboratory, when we make measurements, the individual measurements are never the same. As a matter of common practice, the differences are not ascribed to there being a fuzziness in nature, but to mere errors of observation. Let's use a simple example. Say we are using a ruler to measure the length of a line. Say this line which I've drawn on a piece of paper. Each time we make the measurement, being as careful as possible, we may note a different value, say 2.1 cm, 2 cm, and 2.05 cm. Which is the correct one? Even if we use ever more precise instruments, say vernier calipers or micrometer, we will still encounter different values on each measurement. We can extend this to other experiments, say the kind performed during a chemistry or physics class in secondary school, which is for children of the age of 12 to 16 where I am from. Say we are attempting to use a pendulum to determine the value of the acceleration due to the Earth's gravity, known as small g, which we know from the reference books as 9.81 meters per second squared. We vary the length of the pendulum and measure the period or time taken to complete one oscillation. We then plot our measurements on a graph, the square of the period versus length. Ideally, theoretically, we should get a perfectly straight line going through the origin, since the law governing this is t equals 2 pi square root L over g. In reality, if you could recall your experiences as a student in the physics laboratory, you did not obtain such a line. Even if you are the world's leading experimental physicist, having a lot of experience with conducting experiments, are skilled with the techniques, and are using the best, most precise instrumentation, you will not obtain a straight line. Instead, from the world's best scientist to a 14-year-old student, you will draw what is known as a best fit line, where some data points will fall on either side of this line using the least square method. Peirce, you will recall, is an experimental chemist. He spent many years working in a laboratory setting. Hence, the conduct of science is what he knows a lot about. The pendulum experiment to find small g is not his example. He gives many examples of scientific theories in his Monist papers, some of which may no longer be the leading theories of today since these were written in the 1890s. Hence, I may choose to use other examples I understand better or are simpler to understand, so that his point can come across clearer to a contemporary audience. As we have noted from even the simple experiment of measuring a line with a ruler, it is common practice to attribute the spread we get to errors of observation, but Peirce is suggesting it is not merely error, since such errors cannot be eliminated even with the most precise equipment and the most skilled experimenter. He is suggesting that the laws of nature themselves have imperfect cogency. If you imagine examining the matter of these laws as looking closer and closer at a line drawn on a real piece of paper, you will realize that the line is not as clean and straight as an ideal line should be, but is instead somewhat fuzzy. This fuzziness to Peirce is the nature of reality. Peirce embraces evolution to explain the nature of reality. As a continuous process, this non-mechanistic way of life is literally about life. In Peirce's account of Darwin's theory of evolution by natural selection through chance, evolution takes place because of two factors. 1. Heredity. While offspring mostly resemble their parents, there is room for chance variations. 2. Reproductive success. For species which do not reproduce faster than its death rate, they will ultimately perish. Can evolution itself be a mechanical process? Peirce thinks that this is illogical for 4 reasons. 1. The principle of evolution requires no extraneous cause. The tendencies we observe in things that are attributed to evolution are already themselves caused by evolution. To attribute it to an unchanging mechanical principle would be incorrect. 2. Law ought more than anything else to be supposed a result of evolution. This is an argument Peirce will be making, that the laws of nature today are a result of evolution, not in a mechanical and hence deterministic way, but through the element of chance. 3. Exact law obviously never can reproduce heterogeneity out of homogeneity. Laws of nature, if they work as we have intended, are meant to be able to calculate an outcome precisely, while evolution, because of its chance element, generates outcomes that deviate from the law's predictions. Hence, the way evolution works cannot be mechanical, since being mechanical requires a strict obedience to the laws. According to Peirce, such deviations, arbitrary heterogeneity, is what in fact characterizes the cosmos. 4. The law of the conservation of energy is equivalent to the proposition that all operations governed by mechanical laws are reversible. Since energy cannot be created or destroyed but transformed from one form to another, it seems to imply that any mechanical process is reversible. However, growth in an organic being is not reversible. For example, a plant cannot reverse its growth into becoming its seed. Hence, Peirce considers growth to be a non-energy conservative process. As an aside, it seems Peirce was aware of the second law of thermodynamics, the first law being the conservation of energy, but the second law, which is on entropy or disorder within a closed system, was already known since the 1850s. He may be right to state that the first law, which is the conservation of energy, suggests that all processes are reversible, but the second law prevents such reversibility because of the increase in entropy. Peirce is also a pioneer in the field of statistics and sees the role of statistics in evolution. While there may be a certain trend when there is a large number of a certain thing, this trend, this tendency, is not absolute, but there are variations from the tendency. Large variations are less common, while small variations are common. He does not talk about a bell curve or a normal distribution here, but I think it can be helpful to understand his idea in such a way. While a certain tendency forms the mode of a distribution, meaning many of the members of a group exhibiting a particular characteristic, there are increasingly less and less members as we move away from this norm. Because big chance variations are likely to be less well tolerated in a living thing, small variations are more common. I want to give an example. Imagine in a human being a chance genetic variation leading to having an extra finger versus having an extra arm. An extra finger does not incur a massive load on the rest of the bodily systems, such as its nutritional system, and hence may be easily tolerated, while an extra arm may demand so much from the rest of the body that it is poorly tolerated by its host. Next, Peirce uses a gambling example which is rather fertile but brief. I shall amplify it. Say many gamblers come together to gamble on a coin toss where they have to bet their entire and equal fortune. Let us consider first that the coin is fair. That is, it turns up a more or less equal number of hits as it does tails over many tosses. Still, only after the first round, half the players will be eliminated. After several rounds, much fewer remain than the original number of players. The surviving players will also have by now multiple times their original stake. Just purely on chance alone, after 4 rounds, the remaining players, now only 7.25% of the original number, will have 16 times their original stake. So chance alone already has a way of whittling down the numbers and giving great rewards. He does not elaborate further in this first Monist article, but in an earlier essay entitled Design and Chance, he explains it better. He uses a game of dice, but let's just stick with my coin. To facilitate understanding, let it be just one single coin in that whirl. The coin, after being used for some time, gets worn down in a totally chancy way, where no player went and deliberately buffed it down on one side, for instance. Since chance changes everything, chance will change that, he writes. And say that once it wears a particular way, each subsequent toss will cause it to wear that same way more and more. Let's take it that the way the betting goes is that once a player bets in a particular direction, she has to stick to that bet for all subsequent rounds. So say the coin becomes worn such that it slightly favors hits. Over several rounds, one group, let's call them the headers, will be rapidly separated from the tailers. 2 classes will form increasingly rapidly purely from chance. In such a world, the headers become the champion, the good, following Nietzsche's on the genealogy of morals, while the tailors are the losers and consequently the bad, all merely from chance. What is the moral of Peirce's story? He tells us that Darwin's theory of evolution, which depends on chance as the principal mechanism of evolution, is not the only one. He points at 2 others, the first being Jean-Baptiste Lamarck's around 1800, which predates Darwin's in 1859. Lamarck's theory postulates the driving force of evolution to be the effort of the individuals. Lamarckian animals adapt to their environment during their lifetimes, which will make some more successful than others. These adaptations are then passed on to their offspring, preserving these modifications and hence allowing the advantage to continue. Darwin's theory is less meritocratic. Chance is its operating factor, just like how headers become top dogs in their world with no merit and effort on their part, having just pure dumb luck that caused that coin to become worn and hence bias over time towards coming up heads. Taking things further, Peirce ventures that perhaps all known laws are statistical results. What was at first a result of pure chance, the wearing down of the coin such that a toss would tend towards coming up heads, becomes further and further entrenched until it results in what seems an undeniable rule in that world, that our sole existing coin when tossed will always come up heads. He writes, "Now I will suppose that all known laws are due to chance, and repose upon others less rigid themselves due to chance, and so on in an infinite regress. The further we go back, the more indefinite being the nature of the laws, and in this way we see the possibility of an indefinite approximation to a complete explanation of nature." The coin story illustrates this point. The coin was at first fair. Then comes its first chance encounter. Perhaps the coin fell on a rock which dinged it on one face, making it slightly lighter. At this point, the likelihood of it coming up heads was still only marginally more, say 0.00001% more. Then when the coin was tossed by a human hand, the ding got slightly deeper and deeper because occasionally the tosser's nail cut a bit into the ding. After say 1 billion tosses, the chance of it coming up heads is now 100%. The law in this world will be, the coin when tossed always comes up head, as a physical law of nature. Perhaps another but a social kind of law will be, headers are good, tailors are bad, or headers are destined to be masters, tailors to be the servants of the masters. The moral of the story is, what began as pure chance can end up as a law of nature. Peirce mentions a third theory in addition to Lamarck's and Darwin's. This is Clarence King's in 1877, also after Darwin's. King suggests that species rapidly alter themselves after cataclysms or rapid geological changes. In ordinary circumstances, living things remain unmodified or barely so, but under crisis situations, they adapt rapidly. 3 reasons cause this rapid evolution. 1. Their lives are threatened from being torn from their habitual mode. 2. Change of food. 3. Change of environment. Unlike the theories of the other two, the evolutionary changes for King are substantial and visible. They are not random as driven by chance for Darwin, but also are not due to Lamarck's inward striving. It is caused by a response to the drastic changes in its environment. The variations that are posited affect the organs that are threatened, but at the same time stimulate the rest of the unthreatened body, leading to an evolution caused by external forces. While King's theory has been overshadowed by Darwin's, such biological changes are commonly observed among animals and human beings in response to environmental changes, though they may not be transmitted genetically to future generations. However, King's theory remains useful when applied to the evolution of institutions and ideas, with Peirce suggesting that it may also help explain the evolution of the universe at large. Peirce's article now turns to psychology. He spells out 3 categories of mind: feeling, sensations of reaction, and thoughts. Feelings are what are immediate, a state of mind having its own living quality. His examples are pain, color, and cheerfulness. Next are sensations of reaction. Recall that he is not talking about the body now, but the mind. So by sensations of reactions, he does not mean what is received from our bodily senses, but the sensations in our mind when there is a mental change. These can arise from physical changes, such as when one stubs one's toe, but he is trying to pinpoint what happens when our mind reacts to change. For example, when our feelings of the color blue suddenly give way to red. At the moment of change, in the transition, there is a shock, a sense of reaction. For creatures with memories, this sensation of reaction can continue for a while because of their ability to remember, along with its feeling. So sensations of reaction are about relations between two things which interact. It can even be between something and nothing, of its presence and then its absence. Third is thought. So while we have sensation of reaction from a change in feelings, the connection or relation drawn between the feelings is a thought. This thought is, according to Peirce, governed by a general rule which comes from habit. This habit comes from a tendency to generalization, what Peirce considers to be the primary and fundamental law of mental action. He explains why we generalize, how this habit forms that lead to generalization. Feeling tends to spread, according to him. The connections previously drawn between feelings when triggered awakens the same feelings again. The more it occurs, the easier it is for that feeling to be excited again. Accompanied by the spreading of the feeling, the propensity for a specific excitation in reaction to a specific stimulus constitutes a habit which leads to a generalization. While these mental or psychological notions seem vague, they are connected, or in today's parlance, supervene upon physiological phenomena. Feelings are associated with an excitation in the relevant cells, such as nerve cells. In this way, the mental formation of habits also has a physiological component. However, the psychological component is the basis of habit, making the laws that come out of habit not as absolute as physical laws. Physical laws express an exact relation between their variables, while no exact conformity is required by the mental law. Peirce argues that such exactness will in fact contradict the law. If deterministic causality holds for mental processes, then thoughts will be precise and instantly crystallize, preventing any further formation of new habits. Instead, mental laws are probabilistic, making a certain feeling only more or less likely to occur. This statistical nature of mental laws, moreover, can also be found in physical phenomena such as viscosity. Laws on viscosity only can tell us how an average fluid will behave, but it is not exact for an instance of that fluid, since the law is expressing an average outcome of the random collision of many molecules. As already noted, Peirce predates quantum mechanics, but today an example often given for how physical laws are in actuality statistical will be the half-lives of radioactive elements, where the half-life merely expresses an average for the decomposition of the substance and is not exactly that length for any particular instance of the substance. What then is the relationship between physical and mental laws? Are they independent of each other, what Peirce calls neutralism, or is one of them primordial? If the physical is primordial, with the psychical derived from it, that is materialism. If the psychical is primordial with the physical dependent on it, that is idealism. As you may have already inferred from his discussion on the primacy of psychological law over physical law, Peirce is on the side of the idealist. He refutes the materialist argument since it requires us to suppose that a certain kind of mechanism will feel. How it feels like to be something, that quality that comes from our phenomena feeling, is known as qualia and has come to be known as the hard problem of consciousness, a term formulated by David Chalmers in 1985, but Peirce has already raised it over a century before. The mechanistic worldview fails to explain qualia. Peirce makes an interesting and, in my opinion, important epistemological point here. Theories are supposed to clarify what is observed and be reasonable while it is at it. Materialism does neither, since instead of explaining feeling, it simply makes it a mystery. More contemporary materialistic accounts of philosophy of mind explain qualia or feelings as epiphenomena, an illusion that we think we experience that merely accompanies physical sensations, for seemingly no reason at all, since the material cause already suffices for the subsequent effect. But it fails to answer why we should develop such epiphenomena, why we should evolutionarily develop feelings or qualia when it seems to be unnecessary in their account. Neutralism or dualism also fails, because it makes the inward and outward aspects of substance both equally primordial. Descartes' dualism has been met with a series of objections, one being that two different substances of mind and body cannot communicate, since they are completely different and differently natured things have no way to interact with one another. Yet it seems our minds and bodies are coordinated. Idealism remains, which to Peirce is the only doctrine among the three that is intelligible. It regards matter as effete mind, a weak form of mind, with habits becoming physical laws, which is Peirce's argument that habit begins psychologically and is then manifested physically. However, he concedes that idealism has its work cut out for it, since it needs to be able to explain the laws we have of the physical world, which an extreme idealism denies really exists, except in the mind, and to do so with mathematical clearness and precision. Nonetheless, Peirce's idealism is not an extreme one of the George Berkeley variety, where mind is all that exists, but one where the matter is primary with the material dependent on it. The fuzziness, the statistical, the freedom he ascribes to the mental is to him not merely found only in the mental but also in the physical world. Geometry has for millennia been considered exact and precise knowledge. We have been taught that the internal angles of a triangle add up to 180 degrees. However, whether this is true depends on our conceptions of space. If space is a plane as idealized by Euclid, then the angles indeed add up to 180 degrees. In Euclid's book Elements, written about 300 BC, He starts off by giving us 5 axioms. Axioms are fundamental propositions that are so basic that they cannot be proved and hence have to be accepted as given, as true. He then goes on to construct a system of geometrical propositions with their proofs systematically built up from these axioms, which came to be accepted up until perhaps the 19th century as correct. However, since then, alternate or non-Euclidean geometries have been formulated through modifying the axioms. Peirce's point is that what was considered inviolable, such as Euclid's axioms, have been shown not to be inviolate. If space is spherical, the angles of a triangle exceed 180 degrees, and if space is a circle, the angles are less than 180 degrees. According to Peirce, we do not yet know the shape of space. In experiments measuring a triangle using the Earth's orbit as the base of the triangle and stars as the height, some results have come back with the angles less than 180 degrees. These could be and have been attributed to the excuse of errors of observation. Nonetheless, the point Peirce is making is that there is no certainty on a matter which a layman would have thought was not in doubt. The reason why the angles of a triangle were thought to be 180 degrees is not because it is so, but because they are expressions of our inborn conception of space, what Immanuel Kant calls transcendental idealism, where our conceptions are not how things actually are in reality, but just our way of perceiving them due to the frameworks in our minds. Peirce accepts that reality influences how things are understood by our minds. But even if that influence is in the right direction, there still remains no reason to consider our formulations of the world, the laws we have formulated, to be exact. Philosophy has aped mathematics in trying to imitate the precision and exactitude that mathematics seems to offer. Spinoza, for instance, in his Ethics, sets out his theory in Euclidean fashion, using a geometrical method with the aim of proving the propositions of his theory so as to leave no room for doubt. Peirce writes, "The metaphysical axioms are imitations of the geometrical axioms, and now that the latter, the geometrical axioms, have been thrown overboard, without doubt the former, the metaphysical axioms, will be sent after them." The metaphysical axiom he is attacking here is the tacit understanding we have that the laws of nature are exact, that every phenomenon in all its minutest details is precisely determined by law. He is arguing for the role of chance, based on the intuition that given the variety of things we can observe in the universe, that there must be some element of arbitrariness and spontaneity. As you may have noticed, Peirce has a penchant for patterns to come in threes. For instance, how there are 3 categories of mind: feeling, sensations of reactions, and thought. He calls these triadic patterns first, second, and third. First is of an independent being. Second is the other being, and third is the relation or mediation between the two. This triad is not totally novel. It can simply be thought of as subject being the first, object the second, and their relation being the third, or an agent as first, its objective as second, and the process connecting the agent with its objective as third. In Peirce's view of biology, the first is how the beginning was chaos, where chance was the only factor in any change. Second being heredity, where the chance changes in our genes get transmitted across generations. And third is how what was an accident in the first becomes fixed. More generally, chance is first, law is second, the tendency to take habit is third. He expresses his idealism also in a triadic manner. Mind is first, matter is second, evolution is third. By this, I understand that while he does not deny the existence of matter, what is originary, that is, fundamental or primordial, is mind as the subject, its object being the matter it encounters, and evolution being the relation between mind and matter. He believes this triadic pattern is useful as an architectonic, or a structure to build a philosophical system, and hence expresses his cosmology as such. In the beginning, infinitely remote, there was a chaos of unpersonalized feeling. This feeling, spotting here and there in pure arbitrariness, would have started the germ of a generalizing tendency. Its other spottings would be evanescence, but this would have a growing virtue. Thus the tendency to habit would be started, and from this, with the other principles of evolution, all the regularities of the universe would be evolved. At any time, however, an element of pure chance survives and will remain until the world becomes an absolutely perfect rational and symmetrical system, in which mind is at last crystallized in the infinitely distant future. At the start of the universe, there was just chance. However, even in an environment of pure chance, just merely out of chance, can come some patterns or bias. Consider two series of coin flips, with heads as 1s and tails as 0. The first, 1 0 1 0 1 0 1 0 1 0. The second, 1 1 1 1 0 0 0 0 0 0 0 1 1 1 0 0 0 0 0 1 1 1 1 1. The former, while having as expected from a fair coin the occurrence of half heads and half tails, will be recognized as not random, since a clear pattern can be discerned. The latter, while having runs of heads and also of tails, may in fact be random if no discernible pattern can be discovered as the series proceeds. That is precisely the meaning of random, when no pattern can be discerned. As we can see from the first series, a probability of half is not sufficient to deem it as random. From the second series, we can observe that what is random can develop a streak of ones or zeros, a bias. Coming back to Peirce, so from pure chance alone can emerge a bias, a slant like the slant of the coin from many tosses in the earlier example, out of which becomes a growing virtue, which is subsequently recognized as law-like behavior. This is in fact where we are now, where the habits, the biases or virtues have become so entrenched that we call them laws of nature. He forecasts that as this law-like behavior becomes more and more entrenched, finally the world, all of existence, takes on a perfection, where mind becomes an absolute mind. One may recognize here a resonance with G.W.F. Hegel's conception of absolute spirit as a culmination of the history of the world. Hegel's work had indeed influenced Peirce, as did Kant's, which is no surprise since Peirce has said that to build a systematic theory, a survey of knowledge was necessary. Peirce thinks that such an idea of evolution can not only explain the phenomena of the universe, the laws of nature up to now, but will have predictive power about the future. Thank you for listening to the Philosophical Bachelor.